Just a little bit
Like
the
this?
chin,
Okay,
like
good.
under the chin. Like,
Okay,
yeah, that's fine.
thanks. Hello, everyone. So thanks for the organizer to let me speak here. And the work is with Lyell, my student who double check and sanitize my code. I'll talk about treat today, and this problem that I made is question was asked by a colleague actually. So, and a treat, what is a treat? It's a binary randomized tree. And these definitions are taken from Aragon-Seidel. I list the paper at the end. So a treat is a rooted binary search tree with node set X that is arranged in order with respect to the keys and in heap order with respect to the priorities, okay? Equivalently, we can take a sequence of pairs and then have the keys and the priorities, sort them in decreasing order of priorities and do a binary search insertion on the items with respect to the keys, okay? So I have an example here. So as we can see, the reds are priorities and in green are the keys. So they are in decreasing order of priorities, okay?
Just for future reference, the green.
Yeah, sorry, I will change. For me, it did look well. So, and when I practice on my monitor, I have a similar, but it's not this one at home. It looks better because it's not a kind of carpet style like this. So then we do insert according to the keys, okay? And what we get is this type of example, okay? This type of tree. So we see that the priority satisfy the in order, and then that the priority satisfy the heap order, and then the keys satisfy the binary search order, okay, the in order. So the goal is to de-randomize the data structures because we do assume that priorities are independently and identically distributed, and then it incurs a cost on the storage of data structures. So one of my colleagues says, well, I tried to de-randomize and look the papers, and then I found that doing something that I show you after did work, and I have no proof. So probably I won't get a proof too, but I can try to make sure that it does work in practice. And he did all the stuff in Smalltalk, very old language. So I managed to do everything in C and assembly language just to make sure that things works and work well. So there are a few operations that we can do on these three, like search, insertions. There are many others as and deletion, and there are those operations that I'm interested in. Especially the insertion and the deletion, because we have to do rotations, okay? And what I'm interested in is de-randomizing and making sure that the average number of insertion and deletion for any update is 2, okay? As it is in the case for when we assume that the priorities are IID, okay? So here's a rotation, okay? So we can rotate left. I think you all know that, so I'm gonna go faster. This is taken from Aragon-Seidel, and this is the operations that I'm interested in. I want to de-randomize the structure and keep this number of rotations per date to be 2, okay? So one de-randomization strategy is by taking a seed, okay, in a pseudo-random sequence. So instead of storing about log(n) bits for every node for the priority, we only have to store a seed, which make the things much smaller, but still we need to have a further assumption on the distribution. And these assumptions are related to pairwise and dependent distributions, and in general to, as explained in Aragon-Seidel, to a property called the Dmax property that I've never been through, and I just stated it here, okay? But this is not what my colleague did. My colleague entirely de-randomized a sequence with So I just put it here because there are other connection. I went into these pairwise independent sequence when I did work on polynomial congruential total random generator with Pierre Lecuyer about 15 years ago. And that's why I put it there, because it just reminded me what I've done. There are other strategies to de-randomize and having implicit storage. So on GitHub, there are codes with priorities that use hash functions. There are nodes that can be stored in random order where memory addresses are the nodes, can serve as priorities. We can compute priorities from the size of the subtrees that we need to maintain the size at every node. It incurs an additional cost. Or, and that's what I would like to know, use equidistributed sequences, which is what I've done. And look here at a result about the expected height when we actually use equidistributed sequences. So how does that work? Okay, here I'm not interested in the height of the tree. I'm interested in the number of rotations, okay? So how do we compute the priorities using equidistributed sequences? Well, I'll just recall what is an equidistributed sequences. For that, we need to talk about the torus. I can slip that slide. So if I have a sequence of real number, okay, and what time is it? Okay, good. So I have a real sequence of number. It's equidistributed mod 1 if for alpha beta, such that alpha is less than beta, and both are between 0 and 1. The average numbers of their fractional part is uniformly distributed, okay? Plus something that tends to 0. And we have this notion of discrepancy here. So I just recall what is the discrepancy. So we have this result that was proven by Vail, I think, that if the interval is compact, then the equidistributed sequence, the sequence is equidistributed if and only if the limit of the discrepancy equals 0, okay? There's a nice proof in the book by Gerald Tenenbaum on Introduction to Probabilistic Number Theory. This is where I took the definition. And also I took these results from that book. It's mentioned at the end. I can skip, okay. And because this is what I tried to do to prove, but I wasn't successful in proving it. So I just put the work that I started to work on, and I had no time to go further. So I just wanted to make sure that at least the code that I have is good enough. So first thing, when I did this presentation, people say, well, you're gonna have problem running, you're gonna run into accuracy problem. Yes, okay, I'm gonna fix it. So I took a GMP, for those who know what it is, it's multiple precision arithmetics, and I just set it to 512 bits precision. So I will certainly not exceed a sequence that has length to the 512. And minus 64 because the keys are 64 bits, okay? What I do is exactly as in the Aragon serial paper, I generate a key with a value randomly, okay? If the key is in the treap, I delete it. If the key is in there, I insert it, update the distribution of the counts. And then when I've done that number of n times, I just average. And I tried a few number for the sequence. So I tried the golden ratio. The size of the tree is 2 to the 34. And it takes about 710 gigabytes, which fits on my computer at home. And the total number of operations is, that's 2 to the 34. And the expected number of rotation is 2. I tried this is the Euler constant. Same thing, the number of rotation is 2. I tried the inverse of the number E, same thing here. And okay, maybe conjecture. The expected value of the number of rotations remain 2 when a Vail sequence is used to derive the priorities from the key corresponding, from the value corresponding to the key, okay? And that's why I started to deal with to do the proof, but again, unsuccessful. I need to kind of match this with equidistributed sequences, and I just had no time. And that's it. If you have any question, I can go back on the slide. So hopefully you can get out for lunch, and thank you.